850 horsepower. That is the power output of the hybrid Lamborghini Revuelto. This is almost like having the force of 2 average tanks. Whenever you see a Lamborghini on the road, it is impossible not to turn your head. This is a car that shouts success and style, and it does so very loudly, thanks to its V12 engine. A Lamborghini is not merely an automobile. It is a symbol of status, luxury, and wildly high speed. However, this car is not just beautiful. Its heart is a genuine masterpiece of engineering. Shall I tell you about the engine? Lamborghini is renowned for its naturally aspirated engines that roar like a wild beast. The brand's most famous motors are the legendary V10 and V12, which provide not only insane power, but also an incredible sound that sends chills down your spine. The V12 engine was already present in the first Lamborghini 350 GT from the year 1963, and it remains the company's signature to this day. The establishment of Lamborghini was not merely a business project, it was an act of revenge. In the small town of Sant'Agata Bolognese, under the blazing sun of Emilia-Romagna, a company was born that challenged none other than Ferrari. Ferruccio Lamborghini was a successful businessman who became wealthy through the production of tractors. He owned an entire collection of sports cars, but he had problems with the Ferrari 250 GT because its clutch often broke down. One day, Lamborghini decided to express his dissatisfaction directly to Enzo Ferrari. He proposed improving the cars, but he was met with this response: "Ferruccio, you are just a farmer. You should focus on tractors and stay out of sports cars." Those words were the point of no return. Lamborghini resolved to build his own supercar that would surpass Ferrari. He hired the best engineers, including Giotto Bizzarini, the person who had developed engines for Ferrari. The team created that same legendary engine that became the heart of the first Lamborghini 350 GT. Even then, the car showed that Lamborghini was not joking around. It was faster and more comfortable than Ferrari. The first car was a success, and the company began to grow rapidly. Within only a few years came the legendary Misura, then the Countach, the Diablo, the Murcielago, and the Aventador. And now, for 60 years, Lamborghini has continued to be a symbol of status, aggression, and an engine's ferocious roar. The main Lamborghini factory covers 1,743,752 square feet. That is nearly the size of 23 soccer fields. This place is a genuine temple of speed and engineering artistry. All the critical steps in creating supercars are concentrated here. Massive pavilions equipped with ultra-modern technology merge with the craftsmanship of hand assembly, which remains an unchanging tradition of the brand. The factory includes a materials laboratory where carbon fiber is tested, paint booths where each automobile receives a perfect finish, and the exclusive ad personam division that allows clients to customize their Lamborghinis down to the finest detail. Every vehicle undergoes strict quality tests before leaving this temple of speed, bound for owners all over the world. In the year 2023, Lamborghini set a production record for the entire history of the company. 8,405 brand new cars rolled off the factory line. Every contour of the body is designed not only for aerodynamics, but also for maximum visual impact. The low profile, the aggressive front end, the sharp edges, and the massive air intakes all form the image of a wild predator ready to pounce. The signature guillotine doors on the Aventador or Revuelto models are an unforgettable sight. They lift upward. The moment you open them, you already look like a movie star. Buying a Lamborghini is not simply about money. It is about a way of life. Lamborghini owners want to stand out, be at the center of attention, and experience an adrenaline surge each time they press the gas pedal. It is no surprise that among these owners are soccer players, actors, business people, and even princes. Lamborghini has always been synonymous with exclusivity. Production is limited. Most models are released in small batches, and some appear in limited runs of 10 or 20 units. For example, the Lamborghini Centenario was produced in only 40 units, 20 coupes, and 20 roadsters. Lamborghini uses only premium materials, most of which come from the world's top suppliers. The main material is carbon fiber. Did you assume the body was made of metal? It is not. Carbon fiber is an ultra-strong yet lightweight material made up of extremely thin strands of carbon, each roughly 10 times thinner than a human hair. It is stronger than steel, but weighs several times less, making it ideal for supercars. Carbon fiber begins with polyacrylonitrile threads, which are a synthetic material similar to plastic. The fibers are heated in special furnaces with oxygen, which alters their chemical structure and makes them thermally stable. Then the fibers move into furnaces without oxygen, for instance in a nitrogen atmosphere. Under extreme temperature, they lose all inorganic components and are left as nearly pure carbon. These carbon threads are then treated to bond more effectively with polymer resins. The finished fibers are woven into fabric or laid out as ribbons. The carbon fabric is infused with resin and then shaped as needed. Lamborghini uses forged composites technology, where the fibers are arranged randomly, resulting in parts that are even lighter and stronger. The form goes into a high-temperature, high-pressure autoclave, where the composite hardens and gains extraordinary rigidity. Imagine strands thinner than a hair passing through furnaces at 3,632 degrees Fahrenheit. What comes out is a black thread that is 5 times stronger than steel, yet 7 times lighter. Instead of a conventional steel component weighing 33 pounds, Lamborghini gets a carbon substitute that weighs 6 pounds, while preserving the same strength. This material enables Lamborghini to craft bodies that are light, strong, and fast, reducing the vehicle's overall mass and boosting its aerodynamics and performance. Aluminum is sourced in Europe, especially from Italy and Germany. It is utilized for fabricating the chassis, the load-bearing body components, and various structural parts, since it is both light and strong. Suppliers deliver aluminum as sheets, profiles, or ingots. When it arrives as ingots, it is melted down and cast into blanks. Aluminum is melted in special furnaces at around 2,232 degrees Fahrenheit. The molten metal is poured into molds under high pressure. The casting solidifies in a matter of seconds and is then removed. The cast pieces are ground, excess material is trimmed off, and they undergo heat treatment to enhance their strength. Using aluminum makes the frame about 40% lighter than a steel alternative. Lamborghini's press machines can produce up to about 11,000 short tons of forming pressure. A single aluminum Aventador frame weighs a mere 504 pounds, which is essential for high speeds and maneuverability. Natural Italian leather arrives from renowned tanneries in Tuscany and Piedmont. Alcantara is sourced from a factory in Umbria for the upholstery. Carbon inserts are produced directly at Lamborghini. It may require 7 or even 8 cowhides to upholster the interior of one Lamborghini. Buyers can choose any color of leather via the Ad Personam personalization program. Lamborghini uses premium Napa leather and aniline leather, which both have a natural texture and softness. All leather sections are handcrafted to maintain exclusivity. The leather is manually cut for each part to avoid defects or unevenness. Every seam is also stitched by hand, ensuring precise quality control. Special leather threads are used for this purpose. Each piece is dyed and treated to achieve the requested appearance and texture, consistent with the client's wishes. Once every piece is ready, it is assembled and installed in the automobile. Alcantara is a high-end synthetic material that resembles suede in both look and feel. It is widely applied in the automotive sector. Alcantara is soft, matte, and holds up better to wear than genuine leather. It is also twice as light as leather, which is critical for supercars. It does not fade, retaining its color even under direct sunlight, and it is made of 68% recycled materials. The assembly process begins with preparing the vehicle body and chassis. This involves installing a foundation constructed from lightweight metals or carbon fiber, depending on the specific model. At this stage, every mainframe element is brought together, including the suspension, the exhaust system, and other key components. This step is of the utmost importance, as it lays the groundwork for everything that comes afterward. The body is assembled by hand, using specialized tools and fixtures to ensure maximum precision and minimal gaps. Once the body and chassis are complete, the next step is the installation of the engine and the transmission. The engine is the heart of a Lamborghini, and putting it in place is an exceptionally intricate process. All Lamborghini engines are built and tested separately prior to being mounted in the car. Installing the engine also requires connecting it to the cooling system, the exhaust, and the vehicle's electronics. After this, the gearbox and the transmission system are fitted, allowing the engine's power to be transferred to the wheels. During this phase, all of the vehicle's critical systems are also fine-tuned, including the suspension and braking systems. The following stage involves installing the car's interior parts. This includes the seats, the instrument panels, the door trim, and the steering wheel. All these elements are made by hand using superior quality leather or Alcantara, in the case of sportier versions, along with other exclusive materials. Every piece is finished with meticulous attention to detail, creating a truly unique cabin. For instance, Lamborghini seats are crafted by hand to accommodate every curve of both driver and passenger, providing outstanding comfort. The steering wheel is also handmade and can feature a personalized design, according to the client's preferences. Once the principal interior components are set, the car moves on to the phase dedicated to connecting the electronic systems. Lamborghini cars are noted for their cutting-edge technology, so they come equipped with intricate infotainment setups, navigation, touchscreens, and safety systems. All wires and electronic parts must be hooked up with extreme accuracy to avoid errors or malfunctions. This process can take several hours and calls for highly qualified technicians who precisely follow each component's wiring diagrams. Having finished the physical assembly of the automobile, Lamborghini proceeds with the testing stage. Each vehicle goes through a detailed evaluation on special test stands, where every function and system is checked, ranging from the engine and transmission to the brakes and suspension. This helps detect any faults or issues before the car reaches the end buyer. One of the most vital segments of testing is assessing the car's performance dynamics on the track. Here, the automobile's characteristics at high speeds are evaluated, along with its maneuverability, braking force, and stability when cornering and accelerating. Once all tests have been completed, the car returns to the assembly hall for a final inspection. If all systems operate correctly, the vehicle undergoes one last quality assessment. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. Imagine a machine that can withstand the blast of a high-explosive device, endure fire from automatic weapons, and keep rolling even with shot-through tires. This is the legendary Hummer, designed for the most dangerous missions. From operations in the Persian Gulf to modern combat zones, over 280,000 armored Hummer vehicles have become an essential part of the United States Army. How do these machines go through their testing? Which materials protect the crew? And why do they produce 70 of them per day? Let us find out. To understand why the Hummer became synonymous with invincibility, one should first look back at its history. In the 1980s, the American automobile company called A.M. General unveiled a modified Hummer that was initially developed for the civilian market. However, the troops quickly recognized its advantages for modern warfare, especially on the front lines, where soldier protection is paramount and armored vehicles became critically important for safety. A true breakthrough came after the Hummer became the main transport vehicle for the United States military during operations in the Persian Gulf at the beginning of the 1990s. Since the year 1893, over 280,000 Hummer units have been manufactured. But how can one ensure that this off-roader not only endures harsh conditions, but also provides protection in the most hazardous situations? What exactly sets the military armored Hummer apart from civilian models? Let us see how the armored components are constructed to turn these vehicles into a genuine steel shield on wheels. Military Hummer vehicles use specialized armor materials, including composite armor that combines steel plates with ceramic inserts. These materials can withstand shots from a variety of weapons, including automatic rifles and sniper rifles. Moreover, by incorporating composites, these vehicles are not only armored, but also relatively light for their size. The production rate is around 70 vehicles per day. A key structural element of the armored Hummer is the concept of plus armor. This means that multiple layers of protection are added onto the vehicle, enabling maximum defense in a wide range of combat scenarios. There are also additional design modifications, such as reinforced suspension and strengthened tires, allowing the vehicle to keep moving even if one of the tires has been damaged. Another important aspect is the strengthened floor and roof. In military Hummer vehicles, the floor is structurally protected against blasts. Special materials are used to absorb the shockwave, which reduces risk to the crew if the vehicle encounters a minefield or an explosive device. However, armor is only one part of the overall safety level. Each high-mobility multi-purpose wheeled vehicle, commonly known as the Hummer, consists of over 5,000 parts. Combat Hummer vehicles must not only be protected, they must also be real beasts capable of moving through absolutely any conditions. How is this kind of mobility achieved? In order to preserve high off-road capability and endurance, military Hummer models are equipped with a powerful diesel engine. This engine can generate substantial power that lets the vehicle easily travel through desert sands or mountainous routes, even if there is no road at all. A specialized transmission and adapted rear wheels ensure constant stability in the most extreme conditions. Many modern military Hummer vehicles integrate intelligent control systems that allow the engine and transmission to adapt to the terrain. This significantly boosts maneuverability and endurance during large-scale strategic movements. Armored versions receive steel that is half an inch thick, along with bullet-resistant glass that is 1.5 inches thick. Besides armor, electronic safety systems are vital, such as sensors that detect mines and explosive devices, along with systems designed to remain fire-resistant. They add another layer of protection for the crew, which is particularly critical in combat situations. What else is worth mentioning when talking about armored Hummer vehicles? There are several technical considerations to bear in mind. Military Hummer versions often feature specialized camouflage coatings that help them blend into the environment. This is crucial for enhancing survivability on the battlefield, where every detail can make a difference. Interestingly, the Hummer is not a static vehicle. Its design allows modifications based on mission needs. These can include additional weapon systems, medical equipment, or other specialized modules, depending on the task at hand. A military Hummer can carry up to 2,500 pounds of cargo or tow up to 7,500 pounds. Producing armored Hummer vehicles is a complex and lengthy process that demands highly skilled engineers and advanced technology. Everything starts with meticulous planning. Engineers account for every aspect, from improved mechanical components to resilience during blasts. Multiple prototypes are built, each undergoing a battery of tests. They are dropped from heights, fired upon, and examined for endurance in different conditions. Previously, AM General, the company that originally created the legendary Humvee, was in charge of production. However, in the year 2020, the license to manufacture new military vehicles was granted to Oshkosh Defense. As a result, combat Hummer vehicles are gradually being replaced by the Joint Light Tactical Vehicle, a more modern armored off-road vehicle. Therefore, military and civilian versions are produced separately, using different factories, technologies, and even materials. The body and armored panels are cut using laser or plasma machines, and then they are welded by robots and highly qualified specialists. Precision is crucial, because all seams must be airtight to enhance blast resistance. The Hummer is built on a robust steel frame, designed to withstand high loads. The chassis and engine are assembled separately, then tested for functionality. Only after that are they joined with the body. Once the main parts are put together, the vehicle is fitted with armored panels and additional protection. This stage is time-consuming because every component must be installed with the utmost precision. The interior of a military Hummer is nothing like that of a civilian vehicle. Everything is dedicated to functionality. Some models have air conditioning, which is essential in desert conditions. After assembly, the vehicle is painted with special scratch and corrosion-resistant paints. Several options are employed: desert camouflage for sandy regions, woodland or urban camouflage for the respective environments, and anti-radar coating to reduce visibility on radar systems. This is no ordinary paint. It is formulated to withstand heat, freezing temperatures, and the impact of blasts. The high-mobility multi-purpose wheeled vehicle is not produced in the same way as mass-market civilian cars. It is manufactured in relatively small batches, so fully automated production is impractical. At the same time, certain processes, such as welding and painting, are streamlined by a conveyor system for speed and consistency. Each high-mobility multi-purpose wheeled vehicle is equipped with a 396 cubic inch diesel engine that outputs 190 horsepower. This powerful diesel engine is engineered to operate under extreme conditions. The transmission is a 4-speed automatic adapted for off-road use. The vehicle has permanent four-wheel drive and automatic differential locks. It accelerates to 37 miles per hour in approximately 17 seconds. It is slow, but speed is not the main goal for the military. For military transport, the priorities are off-road performance, reliability, and endurance. The high-mobility multi-purpose wheeled vehicle is not designed for swift maneuvers, but for traveling over any type of terrain. It has a high ground clearance of 16 inches, which allows it to clear rocks, ditches, and logs. Full-time four-wheel drive and differential locks prevent it from getting stuck in mud or sand. The engine and fuel system are protected to withstand fire and blasts. There is minimal onboard electronics, meaning fewer things can break down in the field. It can continue moving on punctured tires. Special inserts allow driving even after the tire has been hit by a bullet. Its payload capacity allows transporting ammunition, injured personnel, and weapons ranging from machine guns to anti-missile systems. It may not be the fastest ride, but it will get you where others simply cannot go. The standard military high-mobility multi-purpose wheeled vehicle initially did not have armor, but since the year 2000, most models have received protection against small arms fire and shrapnel. Configurations vary, from soft body transport versions to the most widespread ones, capable of withstanding a high explosive device blast of up to 13 pounds. There are models with protection systems against chemical, biological, and nuclear weapons. Assembling a single high-mobility multi-purpose wheeled vehicle takes from 3 to 5 days, depending on the armor. At the AM General facility, where they build the high-mobility multi-purpose wheeled vehicle, there can be up to 3,000 workers in one workshop. However, only about 25 or 30 individuals work on assembling a specific vehicle at any given time. These include welders, mechanics, electricians, and armor specialists, each carrying out their tasks at each stage of the production line. The more complex the version, the more time and personnel are required. Before they are shipped, all high-mobility multi-purpose wheeled vehicles undergo 310 miles of test trials across off-road terrain, water, and dust. You already know how the Hummer is painted, but allow me to elaborate on the special matte paint known as chemical agent-resistant coating, which has several important properties. It does not reflect infrared light, making it harder to detect the vehicle with thermal imaging and night vision equipment. It resists chemical attacks. Its formulation makes it easier to wash off hazardous substances following chemical contamination. It withstands scratches and corrosion, enduring impacts from branches, sand, rain, sun, and aggressive liquids. The matte finish eliminates glare, which is critical for battlefield camouflage. The painting process involves multiple layers that are applied to the aluminum body and armored panels. Imagine a motor that can spin up to 23,000 revolutions per minute and produce a level of power that in the past only Formula One race cars could achieve. Now picture that motor installed in your Tesla. How did Tesla manage to create such revolutionary electric motors that have made its cars the fastest in the world? From asynchronous motors to the innovative plaid carbon-wrapped versions, today we will dive into the world of technology that is reshaping the automotive industry forever. Are you ready to discover what is inside the most powerful electric motors of our time? Then let us get going. Asynchronous or induction motors were installed on Tesla Model S and Tesla Model X in their earlier versions. Synchronous motors with permanent magnets are used in Tesla Model 3, Tesla Model Y, and later versions of Model S and Model X. Wound rotor motors represent an enhanced technology that combines the benefits of the previous types. Each of these motors has its own unique aspects in manufacturing. Before initiating production, Tesla engineers design the motor using modern modeling software. The design process considers the materials for magnets and windings, the shape of the rotor and stator for maximum efficiency, the cooling system to prevent overheating, the balance of weight, and the positioning of the motor in the car. After completing digital modeling, prototypes are produced and tested under laboratory conditions. Now let us move on to the stage that focuses on the key components. The first component is the stator. It is the heart of the electric motor and the stationary part of the motor, containing copper wire windings. The stator core is made of many thin layers of electrical steel, which helps reduce energy losses from eddy currents. These steel sheets are cut by laser cutting or stamping. The sheets are assembled together and pressed into the form of the stator. The next step is the coil winding process. Automated winding is utilized, along with a precise calculation of the number of turns. In order to boost efficiency, hollow copper wires with coolant flowing inside are used. After the winding, vacuum impregnation with varnish takes place to protect the windings from overheating and damage. We then proceed to the stator assembly stage. The windings are connected to electrical contacts. Temperature sensors are installed to monitor heating. The completed stator is subjected to quality control and testing. The rotor is the moving part of the motor. Tesla uses two types of rotors. An asynchronous rotor with a squirrel cage is employed in induction motors. It is made of aluminum or copper by casting the metal into a mold. A rotor with permanent magnets is used in Tesla's synchronous motors. It contains magnets based on rare earth metals, creating a strong magnetic field. As with the stator, a multi-layer steel structure is used for manufacturing the rotor. The steel sheets are cut and either glued or pressed together into the shape of the rotor. Neodymium magnets are inserted into the rotor body. The magnets are secured by adhesive or mechanical fasteners so that they can withstand rotational speeds of up to 20,000 revolutions per minute. Because the rotor spins at high velocity, perfect balancing is essential to avoid vibrations. The rotor is tested on specialized equipment that automatically adds or removes material to adjust the balance. The next stage is motor cooling. Tesla employs liquid cooling for its electric motors. Coolant circulates through channels in the motor housing, carrying away excess heat. This enables the motor to function at high power levels. The rotor is mounted on bearings for minimal friction. The stator and rotor are placed inside the motor housing. All components are connected according to the design. A controller operates the motor by regulating power and rotational speed. Metal oxide semiconductor. Field effect transistors, or insulated gate bipolar transistors, are employed to convert electric current. We now move on to the final step, which involves filling the system with cold fluid. The coolant is introduced into the cooling system and checked carefully for leaks. Following assembly, every motor undergoes an extensive battery of tests. A no-load test verifies smooth rotation. A load test evaluates efficiency and energy consumption. A thermal test stresses the motor under maximum loads. A noise test measures noise and vibration. Only after passing all these tests successfully does the motor proceed to the production of Tesla vehicles. Manufacturing Tesla's electric motors is a high-technology process that integrates advanced engineering approaches, automated manufacturing, and sophisticated testing methods. Tesla continually improves its motors, making them more efficient, more compact, and more powerful. This technology lets Tesla produce electric vehicles that outdo the competition in power, range, and reliability. The story of how Tesla developed electric motors for its cars is one of innovative technology, risk-taking, and the relentless efforts of engineers. It all started with an ambitious plan to revolutionize the automotive industry, and although initially the company did not produce its own motors, it ultimately became a leader in this domain. Tesla Motors was founded in the year 2003 by a group of engineers, which included Martin Eberhard, Mark Tarpenning, Ian Wright, Jeffrey Brian Straubel, and the future chief of the company, Elon Musk. The main vision was to create an entirely electric car capable of competing with conventional gasoline-powered vehicles. At that time, electric vehicles did exist, but they were slow and inefficient. That was when the Tesla team decided to utilize an asynchronous electric motor, originally patented by Nikola Tesla in the year 1888. Tesla's first electric motor was developed using technology from a company named AC Propulsion, which was creating high-powered electric motors for electric car prototypes. Tesla established a licensing deal with AC Propulsion and adapted its technology for its first model, the Tesla Roadster of the year 2008. This was a three-phase asynchronous motor featuring a rotating magnetic field. It was manufactured with an aluminum rotor, which provided excellent efficiency. The maximum output was 248 horsepower, enabling the Roadster to accelerate to 61 miles per hour in 3 9/10 seconds. Despite the success of this first vehicle, Tesla encountered difficulties with component supplies. The motors were made at external factories, and quality control was lacking. This pushed the company to consider setting up its own production lines. Transitioning to in-house production took place from the year 2010 to the year 2012. When Tesla started developing the Tesla Model S, it became clear that the company needed to manufacture its own electric motors. There were multiple reasons for this. The first reason was cost, since sourcing motors from external suppliers was expensive. Tesla also wanted a highly efficient motor designed to meet its specific requirements, meaning the design had to be optimized. Quality control was the third reason, because in-house production allowed the company to oversee every aspect of manufacturing. In the year 2010, Tesla purchased a plant in Fremont, California, previously owned by General Motors and Toyota. This was a pivotal milestone in scaling up production. In the year 2012, the Tesla Model S became the company's first vehicle to use Tesla's in-house electric motor. It was more powerful and more efficient than the previous generation's motors. The Tesla Model S motor of the year 2012 represented a breakthrough in technology. It was created using asynchronous induction motor principles, with a copper rotor instead of the aluminum rotor that was in the Roadster. The copper rotor raised efficiency and diminished heat losses. The performance version delivered 416 horsepower, enabling acceleration to 61 miles per hour in 4 4/10 seconds. This model drew global attention, and Tesla expanded rapidly thereafter. Let us examine the newer generations of motors from the year 2017 to the year 2020. Although asynchronous motors remained efficient, Tesla's engineers began exploring new motor designs. In the year 2017, during the development of Tesla Model 3, the company chose to adopt synchronous motors with permanent magnets. The Tesla Model 3 motor, starting in the year 2017, is a synchronous motor with permanent magnets. This made the motor smaller, lighter, and more efficient. Neodymium magnets helped reduce energy consumption. The refined cooling system enhanced reliability. This motor became standard in Tesla Model 3 and Tesla Model Y. However, Tesla did not stop using asynchronous motors and continued installing them on the front axle of Tesla Model S and Tesla Model X for dual-motor versions. Tesla pushed forward and introduced its plaid carbon-wrapped motor technology, which premiered in the year 2021 in Tesla Model S Plaid. Plaid carbon-wrapped motor is a revolutionary solution. It utilizes a carbon wrapping on the rotor, enabling incredibly high speeds of up to 23,000 revolutions per minute. An improved cooling system endures extreme stresses. The Tesla Model S Plaid can accelerate to 61 miles per hour in only 1 99/100 seconds, making it the fastest production electric car in the world. This technology was entirely developed by Tesla's engineering team and is unmatched by any competitors. Manufacturing electric motors for Tesla cars is a sophisticated and advanced process, encompassing pioneering research, modern simulation, automated assembly, and meticulous testing. Tesla gradually evolved from employing asynchronous motors in its early models to integrating state-of-the-art synchronous motors with permanent magnets and the revolutionary plaid carbon-wrapped motor. Through continuous enhancements of its technology, Tesla has produced motors that combine outstanding efficiency, power, and compactness. This enables its electric vehicles to surpass competing models in acceleration, energy consumption, and reliability. Tesla's decision to make electric motors in-house allowed the company to manage quality, reduce costs, and refine designs, proving to be instrumental in its expansion. The unwavering drive toward innovation and the pursuit of new advancements solidify Tesla's role as a leader in electric transportation, shaping the future of the automotive industry. How do you build an engine that can handle temperatures over 3,200 degrees Fahrenheit and carry a Boeing jet across the ocean? Sounds like science fiction, right? But this is the reality of modern engineering. Imagine this. Every single part, from turbine blades to combustion chambers, is crafted with micrometer precision. Metals that don't melt under extreme heat and 3D printing that's changing the game. Dive into the process of creating the heart of an airplane, where every inch truly matters. This is the magic of technology. Turbofan engines that power sky giants like Boeing and Airbus planes might seem like something straight out of a sci-fi movie, but they're the pinnacle of engineering genius. So how do you take tens of thousands of parts and ingredients, almost like puzzle pieces, and turn them into these incredible machines? Ordinary metals simply won't cut it. These engines have to function in conditions where temperatures soar above 1,800 degrees Fahrenheit. That's hellishly hot, and regular steel just can't take it. Enter titanium alloys, lightweight, incredibly strong, and heat-resistant. For the hottest parts of the engine, nickel-based superalloys are used. And trust me, these are no ordinary metals. They're 21st century alchemy. Carbon fiber composites, by the way, are used in the fan blades to reduce weight while maintaining strength. This extreme heat is generated during the combustion process in the engine's combustion chamber, arguably one of the most critical components of a turbofan engine. Here's how it works. Aviation fuel, typically jet fuel, mixes with air and ignites, producing superheated gases. These gases accelerate to insane speeds and temperatures, often exceeding 1,800 degrees Fahrenheit, sometimes even reaching 2,700 degrees in modern engines. This heat is vital for achieving maximum thrust efficiency. The hotter and faster the gases, the more energy they produce to drive the turbine and propel the aircraft forward. Here lies the ultimate challenge. The engine not only needs to endure these extreme conditions, but also perform flawlessly, without a single hiccup. That's why cutting-edge materials like titanium alloys and specialized composites are a must. They can withstand both extreme heat and intense mechanical stress. You know what's truly mind-blowing about making these engines? Even individual components like turbine blades are crafted with micrometer precision. For example, blades are cast in a vacuum to ensure they're free of even the tiniest cracks. Some blades are designed with a single crystal structure, meaning the metal has zero seams. But wait, there's more. 3D printing? Yup, it's used too, especially for intricate parts that traditional casting just can't handle. Turbine blades are the heart of the engine. They operate in the hottest zone, converting the energy from the hot gases into rotational movement. First, a wax model of the blade is created. It's almost like artistic sculpting. Only here, precision down to micrometers is crucial. This wax model is then dipped into a special ceramic solution, which hardens into a strong mold. The wax inside is melted away, leaving a perfect cast for the blade. The ceramic mold is now ready for the most critical stage. Now comes the real show. Superalloys, made of nickel, chromium, and other heat-resistant metals, are melted in a special furnace to temperatures exceeding 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But here's the catch. It's not just about the material, it's about how it's done. To ensure the blade can handle enormous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams, micro cracks, or grains like regular metals do. Why is this important? In these conditions, seams or cracks are like a ticking time bomb. One small flaw, and the blade fails. Single crystals are grown through a slow cooling process. The mold filled with molten metal is gradually lowered into the cooling zone of the furnace. This process can take days, but the result? A blade that's incredibly strong and durable. Once the metal cools, the ceramic mold is broken away, and the blade undergoes meticulous polishing. A special heat-resistant coating may be applied to help it withstand extreme temperatures even longer. And yes, each blade is inspected individually. Even the slightest defect means it won't make the cut. Fuel nozzles, combustion chamber parts, or even compressor blades in aviation are often made using 3D printing. For instance, GE Aviation prints fuel nozzles for its engines that are 25% lighter but 5 times stronger than traditional ones. Layer by layer, using powder and light, components are created that make planes fly faster, farther, and more efficiently. First, engineers create a digital 3D model of the part with maximum precision. Every curve and cavity matters. Why? Because these components often operate in environments where even a millimeter can make all the difference, from engine efficiency to reliability. This digital model becomes a map for the 3D printer, which knows exactly where and how to build the required shape. Instead of a solid chunk of metal, ultra-fine powder, made from titanium, nickel, or Inconel, a super strong aluminum alloy, is used. It looks like sand, but the particles are so tiny they're almost invisible to the naked eye. The powder is loaded into a special reservoir, becoming the building material. The printer's working principle is simple yet genius. It melts the powder using a laser or an electron beam. The laser heats the powder to a temperature where it literally fuses into a solid metal structure. Then, another layer of powder is added, and the process repeats. This method is called selective laser sintering or melting. And here's the cool part. 3D printing can create even the most complex geometric shapes. For example, components with internal cooling channels that simply can't be made using traditional casting or milling. In conventional manufacturing, you often start with a big piece of metal and carve away the excess. It's not only time-consuming, but also expensive because so much material gets wasted. 3D printing flips the script. You only create what's needed, with zero waste. But the part isn't ready yet. After printing, it undergoes heat treatment, heating, and gradually cooling to relieve internal stresses in the metal. Then comes final grinding, polishing, or machining to fine-tune precision. And of course, every part undergoes rigorous testing. Because here's the thing, if a part fails under pressure, the consequences could be catastrophic. Engine assembly takes place in a massive hangar, where every inch of space is filled with tools, engine parts, and technicians in overalls, all focused on creating something extraordinary. This is the final stage of building an aircraft engine. Here, individual components, like blades, compressors, combustion chambers, and casings, come together to form a single unit capable of lifting an airplane into the sky. It all starts with the engine casing, a giant metal cylinder that serves as the skeleton, where everything else is attached. The casing is made from titanium or nickel alloys because it has to withstand insane forces. Engineers work like watchmakers. The casing is mounted on a massive rig to ensure perfect alignment. Then come the compressors, rows of blades responsible for compressing air before it enters the combustion chamber. Each blade is installed one by one, almost like decorating a giant wheel. Every single blade is manually inspected because even the tiniest defect could ruin the entire assembly. After the compressors, it's time for the turbines. These are the blades that convert gas energy into movement. They're installed with such precision that the gap between the blades and the casing is sometimes measured in micrometers. Next comes the combustion chamber, the engine's hell zone. This is where compressed air mixes with fuel and ignites. Engineers install special nozzles to ensure fuel is delivered evenly, and everything here has to be flawless. A nozzle at the wrong angle could reduce efficiency or even cause engine failure. Running through the entire engine is a central shaft. essentially the backbone. At one end of the shaft is a fan, a massive wheel at the front of the engine, and at the other end is the turbine. When the turbine spins from the force of hot gases, the shaft transfers this energy to the fan, which draws in air. Installing the shaft requires specialized robots. This part of the process demands surgical precision, as even the slightest misalignment can cause vibrations that could kill the engine. Once the engine's internal components are assembled, external systems are added. Fuel lines deliver jet fuel to the combustion chamber. The oil system ensures all moving parts are lubricated. And the electronics? The engine is packed with sensors that monitor temperature, pressure, RPMs, and much more. These systems are attached using cables, tubes, and bolts that must withstand both vibration and extreme temperatures. After assembly, the engine isn't immediately installed on a plane. First, it's mounted on a test stand that simulates real flight conditions, from takeoff to turbulence at altitudes close to 33,000 feet. This is the most spectacular stage. Running the engine at full power fills the air with a deafening roar, audible from miles away, and streams of blazing exhaust gases. The engine is pushed to its limits for hours as engineers test its strength, durability, and efficiency. Once the engine passes all tests, it's disassembled. Key components are rechecked, and then it's reassembled for final delivery. The finished engine is packed and shipped to Boeing or Airbus, where it becomes part of a new aircraft. Piece by piece, engineers craft the heart of an airplane, a marvel capable of carrying thousands of passengers across continents. Isn't this a modern masterpiece? Let us know if you'd like to see more videos like this. Think batteries are just boxes that store power? What if I told you it takes nearly 375 tons of rock and over 528,000 gallons of water to produce a single electric vehicle battery? Or that 70% of the world's cobalt is mined under terrible conditions, sometimes by children? In this video, you'll learn not just how lead-acid and lithium-ion batteries are made, but also the environmental impact they leave behind. Ready for some shocking facts that will change the way you see batteries? Let's get started. Car batteries are the heart of modern vehicles. They power the engine start, fuel electrical systems, and in the case of hybrids or electric vehicles, are the primary energy source for motion. But let's dive into their origins. The story of batteries begins back in the 18th century. In 1800, Italian scientist Alessandro Volta invented the first chemical battery, known as the voltaic pile, a far cry from the rechargeable batteries we know today. The first rechargeable batteries were created by French physicist Gaston Planté in 1859. These were lead-acid batteries, and remarkably, they're still widely used in vehicles with internal combustion engines today. The modern production of car batteries is a complex, multi-step process that requires precision and strict quality control. Let's break down the details using the most popular types. Lead-acid and lithium-ion batteries. For lead-acid batteries, the primary materials include lead, lead dioxide, sulfuric acid as the electrolyte, and polypropylene for the casing. Lead is either mined from ore or recovered from used batteries. It's then purified and melted for further use. Recovering lead from old batteries is a process that combines engineering expertise with a touch of modern-day alchemy. First, old batteries are dismantled, crushed in specialized machines, and sorted into lead, plastic, and electrolyte components. Think of it as a high-tech blender that breaks everything down into its core ingredients. The lead components are sent to smelting furnaces, where they're heated to temperatures exceeding 1,100 degrees Fahrenheit. At this stage, the metal transforms into a shiny silver stream that's mesmerizing to watch. Impurities and slag are separated, leaving behind pure lead, ready for new usage. The purified molten lead is poured into molds, where it cools and solidifies into perfectly uniform ingots. These ingots form the foundation for new batteries. The most fascinating part? This lead can be recycled endlessly. It has already lived in previous generations of batteries and might just end up powering your car. Lithium-ion batteries are made from key components like lithium, nickel, cobalt, manganese, graphite, and an electrolyte. Lithium is sourced either from salt flats in South American countries like Chile and Argentina, or from ore deposits in Australia. For lead-acid batteries, the electrodes are crafted from lead plates coated with active materials, specifically lead powder and lead dioxide. Picture this. Molten lead is poured into molds or rolled into thin sheets, which are then cut into precise shapes. These plates often feature multiple holes or grids to enhance bonding with the active material. The active material, which coats the grids, is prepared as a thick paste made from lead powder, water, sulfuric acid, and additives that enhance the chemical reactions. Let's take a closer look. The powder is produced by oxidizing lead in specialized mills, which grind it into a fine dust with the required properties. Watch as the grids move seamlessly along an automated conveyor, where the paste is applied to both sides. Rollers in the machine press the paste into the grids with just the right amount of force, ensuring even coverage and deep penetration into the cells. Excess paste is scraped off with blades, leaving a perfectly smooth layer. These paste-coated grids are then sent into special drying chambers. Inside, the paste loses moisture and hardens, transforming into the active material. We've covered lead-acid batteries. Now let me show you how lithium-ion batteries are made. In lithium-ion batteries, the anodes are made from graphite, while the cathodes are crafted from metal oxides, like lithium cobalt oxide. Next comes the assembly of the battery cells. These are the basic building blocks of the battery. In lead-acid batteries, cells are made by stacking several plates separated by separators. In lithium-ion batteries, the cells can be cylindrical, prismatic, or in pouch cell form. Electrolyte filling is the next step. In lead-acid batteries, a sulfuric acid solution is poured in. For lithium-ion batteries, an electrolyte made from organic solvents ensures the transfer of ions between the electrodes. The finished batteries undergo an initial charge to activate the chemical reactions. Each battery is tested to ensure it meets key parameters such as voltage, capacity, and resistance to discharge. Lead-acid batteries are then encased in polypropylene shells. Lithium-ion batteries, on the other hand, are often assembled into modules, which are later integrated into large battery packs for electric vehicles. Battery production is an energy-intensive process with significant environmental impacts. While lead can be smelted and reused, plastic casings are recycled into new shells, and the electrolyte is neutralized or processed. The situation with lithium-ion batteries, however, is far more challenging. Only about 5% of lithium-ion batteries are recycled. This is due to the complexity of extracting lithium, nickel, and cobalt. But the damage doesn't stop with neutralizing the components. To produce a lithium-ion battery for an electric vehicle weighing about 1,100 pounds, it takes 550,000 pounds of rock and nearly 530,000 gallons of water. This depletes Earth's precious resources. Producing just one EV battery generates anywhere from 3 to 16 tons of carbon dioxide. Imagine that. This is the same amount a gas-powered car emits over 5 years of driving. And that's just from one battery. The most troubling issue, however, is cobalt mining. About 70% of the world's cobalt comes from the Democratic Republic of Congo, where workers, including children, labor under horrific conditions. According to Amnesty International, more than 40,000 children are involved in cobalt mining. To make matters worse, mining often destroys local ecosystems, leaving lasting environmental damage. Recycling lead-acid batteries in countries with low environmental oversight, such as India and China, presents its own set of dangers. Lead dust and acid emissions often escape into the air, creating toxic clouds that harm the health of hundreds of thousands of people. Imagine every tire on your car as the result of decades of innovation, research, and fine-tuned manufacturing. Goodyear, one of the giants in this industry, produces tires that are engineering marvels. But how exactly are these technological masterpieces made? Let's break it down, step by step, and get a sense of the scale of this incredible work. Goodyear was founded back in 1898 and named after Charles Goodyear, the inventor of vulcanized rubber. The production of Goodyear tires begins with carefully selected raw materials. The key ingredient, of course, is rubber. But not just any rubber you'd find in a forest. This is a complex material made from natural rubber and synthetic substitutes. Natural rubber is harvested from the sap of hevea trees grown in tropical regions. This sap is called latex, a familiar term, right? The main suppliers of natural rubber are countries in Southeast Asia, like Thailand, Indonesia, Vietnam, and Malaysia. To collect the sap, neat cuts are made on the bark of hevea trees, similar to how maple syrup is gathered. Latex slowly oozes out and is collected in small containers attached to the tree trunk. A single tree produces only a small amount of latex daily, so plantations are packed with thousands of trees. Initially, latex has a liquid consistency and needs processing. Acids are added to it, causing the latex to coagulate into an elastic mass. Typically, formic acid is used. Yes, formic acid. Sounds surprising, doesn't it? The name dates back to the 1700s, when scientists first extracted this acid from ants. Back then, chemists boiled ants and discovered a liquid with peculiar properties. It turned out to be an acid that many insects, including ants and bees, use as a natural defense mechanism. Today, no one harvests formic acid from ants anymore. Instead, it's synthesized on an industrial scale from chemicals like methanol or carbon monoxide using modern technology. This method is way more efficient than collecting it from insects. Formic acid works perfectly for latex processing because it's non-toxic in small amounts. It easily coagulates the protein molecules in latex, turning the liquid into a solid elastic mass. Plus, it dissolves in water, making it easy to wash away any residue after treatment. After adding the acid, the resulting material is pressed into blocks or rolls and dried. This process significantly reduces its volume for easier transportation. The dried rubber is shipped to factories worldwide. For Goodyear, this includes plants in the United States, Germany, China, and other countries. The rubber is transported by sea in large bales that are easy to store and use in tire production. This covers natural rubber, but how do they make the synthetic kind for tires? Synthetic rubber is an artificially created material made from petroleum products. Its main component is butadiene, a chemical derived from gases left over after refining oil or natural gas. Butadiene, along with other chemicals like styrene, undergoes a process called polymerization. This chemical reaction links molecules into long chains, creating a material with high elasticity. The most common types of synthetic rubber are styrene butadiene rubber and polybutadiene rubber. To give synthetic rubber the properties needed for tires, such as strength, wear resistance, and temperature resilience, special additives are mixed in, like carbon black or silica, and plasticizers. Synthetic rubber is produced on a large industrial scale and shipped to factories in the form of granules, rolls, or preformed blocks. At Goodyear's factories, a rubber compound is created by combining the best qualities of both natural and synthetic rubbers. The rubbers are weighed precisely according to formulas tailored to specific tire models. In massive industrial mixers, the rubbers are blended with other ingredients: carbon black, silica, sulfur, oils, and chemical additives. Think of it like making dough, but under high pressure and heat. During mixing, the rubber turns into a thick black paste. This stage is crucial because it defines the tire's future characteristics: grip, durability, and temperature resistance. The mixture is repeatedly needed to ensure all components are evenly distributed. This guarantees uniformity in the final rubber. After mixing, the material is cooled and formed into large sheets, which are then cut into pieces for further tire production. The process of cutting rubber sheets at the factory is truly impressive in scale. This isn't done with kitchen knives, but with massive industrial machines that work with the precision of jewelers, but on a factory-wide scale. The thickness of the rubber sheets varies depending on the part of the tire they're meant for. For example, the layers for the tread are thicker than those for the sidewalls. Before cutting, each roll or sheet passes through an automated inspection system. Machines check for defects like air bubbles, tears, or uneven thickness. Anything that doesn't meet standards is immediately discarded. Cutting is done using specialized high-tech machines. Rotary knives, resembling spinning discs, effortlessly slice through the rubber, creating perfectly straight strips. Lasers, the most advanced technology, can cut rubber without physical contact, ensuring extraordinary precision. The laser beam literally melts the material at the desired spot, leaving a flawlessly smooth edge. Depending on the production stage, sheets may be cut into long, narrow strips for tire reinforcement or left in large pieces for the tread. Everything is programmed, and parameters are automatically adjusted based on the type of tire being made. After cutting, materials are sorted by type and size. Strips are rolled up, and sheets are stacked. All of this is transported to the next department for tire assembly. Each machine processes thousands of feet of rubber daily. Powerful engines roar, knives spin at incredible speeds, and workers monitor everything through computers. This conveyor never stops, producing hundreds of tires every hour. It's like surgery on an industrial scale. Everything must be flawlessly precise to ensure the finished tire is safe and high quality. Goodyear is one of the world's leading tire manufacturers, with production facilities in 22 countries and 52 factories. Let's circle back to another fascinating aspect of this story: the ingredients beyond rubber. Why are they added? Carbon black gives the tire strength and protection against UV rays. Silica improves road grip, especially in wet conditions. Sulfur and other chemicals help rubber retain its shape and elasticity under different conditions. As you can see, every detail matters. But that's not all. Let me tell you about the skeleton of the tire. You know it's not just rubber, right? The core consists of a multi-layered structure. The quality of this framework determines the tire's strength, durability, and ability to support the weight of the vehicle. This process involves several sequential and high-tech operations. But first, let's look at the materials. Textile cords are a must in the tire's construction. These are threads made of polyester, nylon, or even aramid, a highly durable synthetic fiber. They provide flexibility and lightness. Steel cords are also added. These are thin yet incredibly strong metal wires that give the framework rigidity and the ability to withstand heavy loads. Rubber acts as the bonding material between the layers of cord, creating a strong yet elastic structure. Cords pass through specialized machines that evenly coat them with rubber. This binds the fibers together, protects the textile or metal from moisture and corrosion, and ensures a strong bond with other rubber layers during vulcanization. This process is incredibly precise. If the rubber layer is too thick or too thin, it could compromise the tire's safety. Next comes the breaker. This part of the framework lies between the tread and the tire's core. Its job is to distribute the load across the tire and protect it from punctures. The breaker is made of multiple layers of steel cord laid at specific angles. Each layer is cut to a template and laid out in a precise sequence on specialized drums. The angles are computer-controlled to achieve the desired characteristics. The main framework is assembled on a special building drum that rotates, allowing all layers to be evenly laid out. First, textile layers are added for flexibility. Then, metal wire rings are added to form rigid sidewalls. These rings help the tire stay firmly on the rim. The tire bead, its inner edge that contacts the wheel, must be extremely strong. The bead ring is made from multi-layered steel strips coated in rubber. Side layers of rubber are added to the main framework to protect the tire from damage. This entire sandwich is secured on the drum using pressure and heat. Every single day, millions of batteries end up in landfills, posing a serious threat to the environment. But what if I told you those old batteries hold rare metals that can power the technologies of tomorrow? lithium for electric vehicles, nickel for wind turbines, cobalt for medical devices, all hidden within the process of recycling. Want to know how toxic waste transforms into resources for the future? Stick around. An incredible process awaits. Battery collection starts with people. Individuals drop off batteries from phones and laptops. Auto repair shops contribute electric vehicle batteries, and businesses with lots of equipment also pitch in. Collection points can be found in electronics stores, supermarkets, or specialized recycling centers. This process is mostly hands-on. People bring in batteries, and staff or volunteers accept and log them. Large volumes of batteries from factories or auto repair shops are delivered by trucks to major collection centers. Specialized battery containers come equipped with sensors to detect their fill level. When a container is nearly full, it sends a signal to the recycling company. Some companies even use drones to check the status of large containers in remote locations. Batteries are sorted by type using both people and machines, as different batteries, like lithium-ion, nickel metal hydride, or lead acid, can't be recycled together. At smaller collection points, like those in cities, workers manually sort batteries by examining labels, markings, and physical characteristics such as shape or color. Small batteries from smartphones or laptops are sorted one way, while larger electric vehicle batteries take a different path. At larger facilities, automated sorting lines take over. Machines scan batteries based on their size, weight, and the metals they contain. Advanced tools like X-ray analysis or spectroscopy determine the type of battery in front of them. Once scanned, batteries move along conveyors into designated bins, where they wait for the next stage. Even at automated factories, people are still part of the process. Operators ensure machines are sorting batteries correctly. If a problem arises, like a damaged battery case or missing label, workers step in to sort them manually. Batteries from electric vehicles or solar power systems are often too large for automated lines. This is where robots come in, helping dismantle these massive units into smaller sections, which are then sorted by material. No matter how much machines can do, people are still the heart of the sorting process. Most of the work is handled by employees at collection points and operators of sorting lines. Experts manually inspect damaged batteries, because machines haven't yet mastered the ability to detect every defect. Sure, machines are faster, but we can't do without human oversight just yet. In the end, every properly sorted battery is another chance to recover rare earth metals and reduce environmental harm. Next up, the batteries get shredded, like entering a pair of massive steel jaws. They're loaded into a machine that looks like a giant shredder, armed with industrial-grade steel blades. These blades are so powerful they can tear apart an electric vehicle's battery casing. The scene is pure metallic chaos. The sound of ripping, grinding, and snapping as the batteries are literally torn to pieces. Since batteries may still hold a charge, they're first frozen in liquid nitrogen. This cools the metals and minimizes the risk of fire. Some shredders operate in sealed chambers filled with inert gases to prevent contact with oxygen. There's even a more dramatic approach. In some facilities, batteries are burned with controlled electrical currents, leaving only the metals behind. The batteries are shredded into pieces ranging from several inches to fine powder, depending on the type of shredder. The blades spin at over 2,000 revolutions per minute, sending metal fragments clanging and crashing inside a protective chamber. The shredded material then moves through magnetic separators, which precisely extract ferromagnetic metals like nickel or cobalt. The remaining fragments continue along the conveyor belt. A fine black powder, known as black mass, settles into specialized containers. This is where the real treasure lies: lithium, cobalt, and manganese. Machines use dust collectors to literally suck up the powder, ensuring even the tiniest particles are recovered. The remaining materials that can't be recycled, plastics and traces of electrolytes, are flushed out using specialized liquid streams. At this stage, hydraulic crushers grind the leftovers into a slurry that's easy to filter. Engineers monitor the crushers and the temperature inside the chambers. Specialists analyze the crushed material to ensure all metals have been separated and no unwanted contaminants remain. If a battery is still charged or has defects, it can literally explode during crushing. But don't worry, the system has it under control. Any explosion is immediately suppressed with gases, and the process keeps running smoothly. Once the batteries are shredded and that precious black powder is collected, the real magic, science in action, begins. Metals that seemed locked away forever are recovered using two main methods: hydrometallurgy and pyrometallurgy. It might sound a bit technical, but the processes themselves are fascinating. So, how does it work? The battery fragments are submerged in special acidic solutions. Imagine massive vats filled with bubbling yellow-green liquid, typically sulfuric or hydrochloric acid. When the fragments are immersed, a chemical reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve into this metallic soup. To extract specific metals, a clever trick called ion extraction is used. Special reagents, such as organic compounds, are added to the solution. These reagents act like magnets, binding to particular metals. The result? Each metal settles into a separate layer. Once the metals are isolated, they're precipitated as salts or hydroxides. These appear as tiny white or colored crystals. For example, lithium settles as lithium carbonate, resembling fine sugar. Cobalt forms a vibrant blue precipitate, while nickel becomes a pale green powder. If hydrometallurgy is the gentle approach, pyrometallurgy is more like shock therapy for metals. Everything here burns and melts. The black mass is loaded into a massive electric arc furnace, where temperatures soar to nearly 3,000 degrees Fahrenheit. The metals liquefy into molten layers, while plastic and other remnants simply burn away. The metals separate naturally, like oil and water, but at lava-like temperatures. Inside the furnace, several layers form. Heavy metals like cobalt and nickel sink to the bottom, while lithium remains in the slag, the lighter, upper layer. This slag is then broken apart and processed separately to extract lithium. Once cooled, the metals take the form of small ingots, shiny, smooth, and ready for reuse. Cooling after the pyrometallurgical process is typically a controlled procedure. If molten metals are left to cool on their own, it could take hours or even days. Plus, uneven cooling can lead to structural irregularities, which compromise the quality of the final product. That's why specialized chambers are used to regulate the cooling speed. For air cooling, ingots are placed on a conveyor under powerful fans. Imagine a giant hairdryer quickly cooling the metal surface. For water cooling, the ingots are submerged in tanks filled with water or special liquids for a faster process. As the red-hot ingots hit the water, they release dramatic clouds of steam, a visually stunning sight. There's also hybrid cooling, where the process starts with air cooling and finishes with water immersion. This method reduces internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse in batteries. It minimizes cracks or defects that can occur due to rapid temperature shifts. The extracted lithium is used to create new batteries, ones that will power electric cars or even your phone. Nickel becomes part of wind turbines generating clean energy, while cobalt plays a vital role in medical devices. This process literally closes the loop. Old batteries give life to new technologies. Discarded batteries can become an ecological disaster. First, they contain toxic substances that contaminate soil and water. Second, mining for new rare earth metals not only depletes natural resources, but also damages the environment. Recycling solves both problems. Here's the kicker. The more batteries we recycle, the less we rely on mining new materials. It's a direct path to sustainable development. Despite lithium's growing popularity, only 1% of this metal is currently recycled. The main reasons: high costs and the complexity of the process. But researchers are developing new technologies that could revolutionize this in the coming years. Interestingly, even now, electric vehicle manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to keep control over these valuable materials. Every year, more than 12 million cars are scrapped worldwide, and this has become a massive industry running like clockwork. Imagine this. Your old ride could turn into a brand new skyscraper, and that worn-out engine might end up in a military battleship. But what actually happens to cars that have reached the end of the road? They are not simply tossed away. 90% of their materials get recycled. How are cars dismantled, crushed, and literally torn apart to be turned into something new? Today, we are taking a deep dive into this process. Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal. Unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle. but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns: oil leaks, gasoline spills, lead contamination. Gasoline still contained lead back then, and other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, they are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Imagine a place where the trains of the future are born every single day, a place that brings together innovation, sustainability, and history. The Siemens Mobility Factory in Sacramento is over 2 million square feet of manufacturing space, creating the locomotives that move America. Here, one of the largest 3D printers in the world is installed, and up to 80% of the energy comes from solar panels. Curious about how trains are tested? They are run on specialized tracks to evaluate speed, noise, and stability. This is not just a factory, it is a true innovation lab. The story of this factory began back in 1984, when Siemens decided to invest in the future of rail transport in the United States. But they needed more than just technology. They needed a reliable base, and Sacramento was the perfect choice. What does the capital of California have to do with train manufacturing? Actually, the location choice was very strategic. Sacramento has a long history of railroad infrastructure. As far back as the 19th century, this city was one of the key hubs of the Transcontinental Railroad. In other words, the railway spirit has been alive here for over 150 years. Additionally, the region had access to a large number of skilled workers who could contribute to manufacturing. On top of that, the proximity to ports and other transportation hubs in California ensured smooth logistics. When the factory first opened, it was relatively small. Siemens Mobility was just beginning to build its brand in the United States. Initially, the factory specialized in manufacturing locomotives and trams. However, the company's ambitions were massive. They saw the need for modernizing American rail transport and decided to become part of this revolution. Within just a few years, the factory began scaling up production while implementing cutting-edge technologies. Over time, it started producing trains that you can now see in dozens of American cities. The Siemens Mobility factory continued to grow. In the 2000s, it began producing modern high-speed trains and electric trains that meet the highest standards of comfort and energy efficiency. One of the key milestones was the expansion of the manufacturing facilities. The factory grew to over 200,000 square meters. This allowed for increased production capacity, the addition of new car manufacturing lines, and even testing grounds. Today, the Siemens factory in Sacramento is one of the most sustainable manufacturing sites in the world. Approximately 80% of its energy comes from on-site solar panels. Water usage is maximized for efficiency, and nearly all material waste is recycled. By the way, this factory produces trains for Amtrak, Brightline, and various urban rail systems, including the Los Angeles Metro and Minneapolis streetcars. The factory emphasizes localization. About 90% of the materials used in train manufacturing are supplied by American companies. This not only reduces logistics costs, but also supports the local economy, enables quicker responses to market needs, and ensures that the products meet client requirements. Siemens Mobility does not stop innovating. They are already working on trains with hydrogen engines and autonomous driving systems. While specific statistics on these projects may be limited due to commercial confidentiality, it is known that the company invests significant resources in research and development in these areas. So, how are trains made? It all starts with large sheets of aluminum and steel, which are cut and formed into components for train cars. And you know what? I was amazed by how organized the process is. Even at the stage where you are just looking at pieces of metal, everything is planned down to the smallest detail. Assembling a single car can take weeks, and an entire train, months. But the result is worth it. When they arrive at the factory, they are immediately distributed into zones based on what will be made from them: walls, floors, roofs, or smaller components. This is not just a pile of metal. It is all sorted and labeled with special codes. This ensures that no piece gets lost and that production does not halt due to confusion. The metal is cut on specialized machines that use lasers or plasma cutting, and there is no room for error. Every piece is cut with millimeter precision. But here is the interesting part. There is almost no waste. Leftover pieces are reused to create smaller components or sent for recycling. This is not just cost-saving, it is sustainable. The metal is used, for instance, to create train car exteriors. These are made of aluminum for a good reason. This material is both lightweight and strong, making it ideal for high-speed trains. I was even told that it is environmentally friendly. Aluminum can be recycled almost infinitely. Impressive, right? Cutting robots and hydraulic presses create parts that undergo further processing. Everything here is ultra-precise. There is no eyeballing it. In the next workshop, the train's frame is welded. Once the car bodies are ready, robots and highly skilled workers step in. I watched as each part was installed one by one, from roofs to floors, from walls to doors. It is like a massive Lego set, but on a scale you can hardly imagine. In this workshop, the car frame is born. Every weld is checked to ensure it can withstand future loads. Imagine sparks, bright lights, and sounds like in a blacksmith shop, but with robots. Workers install windows, doors, seats, electrical systems, ventilation, everything that makes a train comfortable for passengers. Next, the train is painted with weather-resistant paint. And yes, everything here is as eco-friendly as possible. Filters capture harmful substances to prevent environmental damage. But the most fascinating part starts with the details. Did you know that every train car interior is essentially a small universe? Wiring, control systems, air conditioning, seats, everything is installed with meticulous precision. One worker even joked, "Every single screw here is worth its weight in gold." Another thing that amazed me was how many processes are automated. For example, electronics inside the cars are tested using special simulators. It is like a video game where the system checks if all buttons, displays, and even Wi-Fi are working. Now picture this. Before a train hits the tracks, it is tested on a special track. Yes, they literally run it here to measure speed, stability, and even noise levels. Watching this giant accelerate is a whole new level of satisfaction. Here is what makes factories like Siemens Mobility special. Everything works in harmony. On one hand, there are people working with their hands, putting a piece of themselves into every car. On the other hand, there are robots and automated systems making the process faster and more precise. I was even shown one of the largest 3D printers in the world, which prints train parts. Imagine this. Instead of waiting for parts to be delivered from across the globe, the factory can make them right here, right now. It is not only convenient, but also eco-friendly. Less transportation means fewer emissions. For instance, the 3D printer produces mounting nodes, frame elements, and even special ventilation components. Traditionally, these would need to be cast or welded, but here everything is done more precisely, faster, and more efficiently. Fairings, structural components, interior details, spare parts, and prototype versions of parts can all be printed, saving materials and time. Okay, some might ask, what is so special about this? Trains are just trains. But no, each of these modern cars is a step forward in transportation development. More sustainable materials, energy-efficient systems, passenger comfort, all of this impacts not just us, but the future of our planet. Moreover, factories like the one in Sacramento create jobs and introduce new technologies that can later be applied in other industries. It is a place where technology and people come together to create something truly remarkable. Oh, you cannot even imagine how massive this factory is. The Siemens Mobility facility in Sacramento spans approximately 2 million square feet. Picture several football fields connected into one giant structure. It is a city within itself. Workshops, conveyors, rail tracks, repair shops, and even test tracks for finished trains. The factory is divided into several zones, each responsible for a specific stage of production. When I left the factory, I felt like I had visited the future. This is a place where innovation, craftsmanship, and human talent combine. If you ever get a chance to visit something like this, do not miss it. It is truly impressive and changes how you see the world. So, are you ready to hop on a train next time and think, how was this made? What do rockets and a fabric stronger than steel yet lighter than plastic have in common? And how do engineers create technology that withstands 17 million pounds of thrust, the freezing cold of space, and temperatures in the thousands of degrees? Today, we'll uncover the secrets behind rocket construction, from revolutionary materials to million-dollar final tests. Get ready, this journey will leave you in awe. First off, a rocket isn't just a metal cylinder with engines, as it might seem at first glance. Turns out, many of its components are made of advanced materials called supermaterials. Take carbon fibers, for instance. They're incredible. Imagine a fabric that's lighter than plastic, but stronger than steel. These fibers are woven into thin layers, almost like a carpet, then infused with special resins and baked. This process creates the rocket's body, capable of withstanding extreme stress. Picture this. In just 1 square inch of carbon fiber, There can be up to 50,000 individual fibers. Each one is only a few micrometers thick. That's thinner than a human hair. Let's dive deeper. Carbon fibers are made from a polymer called polyacrylonitrile, or from carbon residue in petroleum. The process begins with long, thin threads of this polymer. These threads are heated to extraordinarily high temperatures, up to 5,500 degrees Fahrenheit. During this process, organic components are removed, leaving nearly pure carbon composed of tiny yet incredibly strong crystals. These crystals in carbon fibers are aligned in one direction, like perfectly arranged bricks in a wall. This alignment gives the fibers extraordinary tensile strength. Plus, they're highly heat resistant, making them perfect for the harsh conditions of space, where temperatures can swing by hundreds of thousands of degrees in either direction. For rockets like the Falcon 9 from SpaceX, carbon fibers are often combined with epoxy resin to create composite materials. These composites are used for fuel tanks, bodies, and even protective shells, anything that needs to be strong yet lightweight. Carbon fibers are produced in specialized factories, most of which are located in Japan, the United States, and Europe. Companies like Toray Industries and Hexcel are leaders in this field. From these factories, the fibers are shipped to facilities where rockets are built. The weaving of carbon fibers happens on specialized machines called automatic winding machines or robotic braiding systems. At the center of the process is a massive mold shaped like a cylinder or cone, which becomes the rocket's body. Fibers are carefully wound around this mold. The winding isn't random, it's precisely calculated. Layers of fibers are laid at different angles to ensure maximum strength and resistance to stress. It's similar to making plywood, multiple layers with different grain orientations, but on a nanotechnology level. This research took me a long time, and I pieced together this video frame by frame over several weeks to show you. I hope you enjoy it. Now, let's see what happens next. After the body is woven, it's time for the resin. Resin is evenly applied to the fibers to create a strong composite. Think of it as gluing layers of paper together, except instead of paper, you have carbon fibers, and instead of glue, you have specialized polymer resins. Once the body is ready, it goes into a massive oven called an autoclave. Here, at about 400 degrees Fahrenheit and under high pressure, the resin hardens into an ultra-strong material. This step is critical because, without it, the body couldn't withstand the enormous stresses and temperatures during a rocket launch. This process typically happens in specialized hangars or production facilities. For example, SpaceX's Gigafactory, enormous, immaculately clean spaces. Robots and automated systems control everything to ensure not a single speck of dust interferes with creating the perfect rocket body. The size of the machines and molds is staggering. Imagine a cylinder tens of feet long and several feet in diameter. Access to these top-secret facilities is required to witness this incredible machinery in action. They say it's a sight that's out of this world. As you might guess, I couldn't see everything with my own eyes. The completed SpaceX Falcon Heavy rocket is 230 feet of pure engineering brilliance. It weighs over 3 million pounds, that's the weight of about 7 blue whales, and can lift 140,000 pounds of cargo into orbit, more than a fully loaded Boeing 737 with passengers, fuel, and luggage. Titanium and aluminum alloys are the foundation for many rocket components that require a combination of lightness, strength, and resistance to extreme temperatures. Fuel tanks must withstand immense pressure and temperature changes since they store cryogenic liquids. Aluminum lithium alloys, which are lightweight yet incredibly strong, are often used for this purpose. Turbopumps frequently use titanium. It's not only strong, but also highly corrosion resistant, which is crucial since these components constantly interact with aggressive substances like rocket fuel. The rocket's frame, as well as various mounts and connectors, are often made from aluminum alloys to reduce the rocket's overall weight. But when additional strength is needed, or components face extreme loads, titanium is the go-to material. Some engine parts, such as combustion chambers or structural components, can also be made from titanium alloys. They handle high temperatures and vibrations during engine operation with ease. For reusable rockets like the Falcon 9, titanium is used for legs and parts that ensure reliable landings. For example, the famous titanium grid fins of the Falcon 9 allow the rocket to adjust its trajectory during re-entry. In short, these metals are like the skeleton and muscles of the rocket. One provides lightness, the other unparalleled strength. Next, we were taken to a workshop where every inch seemed to breathe technology. Honestly, I initially thought I had stepped onto a sci-fi movie set. Robotic arms, lasers, and 3D printers, creating components from metal powder, all working together like a symphony. These 3D printers are a game changer. Instead of cutting components from blocks of metal, they build them layer by layer. What's fascinating is that this not only saves time, but also allows for shapes that were previously impossible to create. For example, internal parts of fuel pumps are now printed as complex grids, making them lighter and more efficient. And now, the most exciting part: final assembly. Rockets are assembled step by step: the lower stage, middle, and upper stage. Every segment is inspected and tested for proper fitting. Engines are a story of their own. They're installed last, like crown jewels. And these engines, they're engineering marvels. They generate incredible thrust while operating with the precision of a Swiss watch. Each rocket comprises over 100,000 individual components. Every single one must work flawlessly, because even the smallest mistake can turn a billion-dollar project into a pile of scrap metal. Some rocket components are assembled in rooms cleaner than hospital operating theaters. For instance, satellites or optical instruments are built in clean rooms where air is filtered to remove even the tiniest particles of dust. The staff wears protective suits because even a single speck of dust could damage the electronics or optics meant to function in outer space. Once assembly is complete, the rocket undergoes a series of tests. Picture a massive platform where the rocket is secured and ignited at minimal power. Engineers check everything, from tank pressure to engine behavior. One of the most fascinating steps is simulation. Special chambers recreate space conditions: vacuum, low temperatures, and radiation. The rocket must prove it's ready for any challenge. Each rocket launch can cost up to $100 million, roughly the price of 50 Ferraris for just one moment in space. Impressive, isn't it? The sound wave from a rocket launch is so powerful, it can destroy not just buildings, but the rocket itself. That's why facilities like NASA or SpaceX conduct acoustic tests. Rockets or individual components are placed in special chambers where massive speakers and water cooling systems create a sound that mimics a launch. This ensures the rocket's parts won't break under the immense sound pressure. Acoustic tests are mind-blowing. Imagine a sound exceeding 160 decibels. For context, human pain starts at 120 decibels. These powerful speakers literally bombard the rocket with sound to check if its components can withstand the pressure. Finally, after months or even years of work, launch day arrives. Standing in front of a massive monitor, I felt the world come to a halt. The countdown, the roar of the engines, the clouds of smoke, and the rocket rises into the sky, leaving a fiery trail behind. This is the moment when every bolt, every detail, and the efforts of hundreds of people come together. When a rocket launches, its engines generate over 17 million pounds of thrust, enough to lift an entire island or power a small town for an hour. Before a rocket launch, tons of water are poured under the launch pad. And no, it's not to put out fires, it's to reduce sound pressure. Without this, the acoustic wave from the launch would be so strong it could damage the rocket within seconds of liftoff. When I first set foot in this facility, I had no idea how much work and innovation goes into every launch. But now, sharing all this with you, I'm even more in awe of what human imagination can achieve. Rockets are a true symbol of how far we can go when we set ambitious goals. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress, so there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. Every single day, airplanes across the world consume more than 5 million barrels of aviation fuel. This fuel is the lifeblood of aviation. Without it, not a single jetliner would take off. But have you ever wondered how it is made? From oil refineries to the ultra-pure tanks inside aircraft, the journey of jet fuel is packed with chemical secrets, strict regulations, and even technologies originally developed for military fighter jets. Today, we are pulling back the curtain on this fascinating process and uncovering all its secrets. Jet fuel is a crucial component of the aviation industry. It must meet stringent quality standards to ensure the stable operation of both turbojet and turboprop engines. The primary source for jet fuel production is crude oil, which undergoes a complex technological journey from extraction to the final product. It was obtained through the distillation of crude oil. In the year 1903, the Wright brothers made the first controlled flight with the Wright Flyer, powered by a gasoline engine. In the early days of aviation, gasoline remained the primary fuel, as piston aircraft engines required a high degree of fuel volatility. However, during the 1920s and 1930s, engineers began considering kerosene as an alternative to gasoline due to its higher energy density, making it more suitable for high-altitude flights. German engineer Hans von Ohain and British designer Frank Whittle independently developed the first operational jet engines. Can you believe it? It is true what they say. Ideas are in the air. So, in the year 1939, Germany tested the first jet aircraft, the Heinkel He 178, which ran on specially refined kerosene. In the year 1941, Britain responded to the Nazis by launching the Gloucester E into production, the first British jet aircraft. Around the same time, engineers began developing special types of kerosene that met the demands of jet engines. Military nations involved in the war experimented with various fuel formulations to ensure high energy density, resistance to low temperatures, and low corrosiveness for fuel systems. During the war, jet fuel had a primitive composition, but over time, its standards improved significantly. After the devastating Second World War, jet aviation began rapidly advancing. This created a demand for improved fuel that could provide reliability at high altitudes, better thermal stability, and the absence of harmful impurities. In the 1950s, the first standardized types of jet fuel emerged. Let's take a look at them. JP1, developed in the year 1944, was an early standard for military aviation. JP4, introduced in the year 1950, was a blend of kerosene and gasoline that improved performance in cold temperatures. JP5, introduced in the year 1952, had a higher flash point and was used on US aircraft carriers. Commercial aviation also introduced its own standards, and in the 1950s, Jet A and Jet A1 were introduced as the primary fuels for commercial aircraft. With the development of supersonic aviation, such as the Concorde, and new generation military aircraft, the demand for higher quality fuel increased. Fuel now needed a lower freezing point, as flights took place at extremely high altitudes. This led to the introduction of anti-static and anti-corrosion additives, improving safety. Fuel systems were also designed to prevent icing, as jet fuel could cool down to -40 degrees Fahrenheit or lower. In the 1980s, the military adopted JP8, replacing JP4. This new standard contained fewer volatile components, making it safer to store and transport. The 1990s marked the beginning of the modern era of jet fuel production. So, let's move on to the steps involved in making jet fuel today, starting with crude oil extraction. Jet fuel is derived from hydrocarbons found in crude oil or natural gas. There are several methods for extracting crude oil. The first method is natural pressure extraction, where oil flows to the surface due to its own pressure. This is common in young oil fields. The second method is mechanical pumping, where pumps are used to lift the liquid to the surface. The third method is secondary recovery, where water or gas is injected into the reservoir to increase pressure and stimulate oil flow. Once extracted, crude oil contains impurities such as water, gases, and solid particles that must be removed before refining. Before transportation to the refinery, crude oil undergoes purification. First, water is separated using separators and chemical agents to remove emulsions. Next, degassing removes light gaseous hydrocarbons. Finally, filtration removes solid particles. In storage tanks, the flow slows down, allowing heavier particles to settle, while lighter fractions rise to the top. After this preparation, crude oil is transported to refineries through pipelines or by tanker ships. The next step is the separation of crude oil into different fractions. Let me explain how this process works. The process begins by heating crude oil to temperatures between 662 and 752 degrees Fahrenheit inside a massive distillation column. Through evaporation and condensation, we obtain different fractions: gaseous hydrocarbons, gasoline, kerosene, diesel fuel, and residual fuel oil. The gaseous hydrocarbons include methane, ethane, propane, and butane. The kerosene fraction serves as the primary raw material for jet fuel and undergoes further purification. To improve the quality of the kerosene fraction, it is treated to remove sulfur, nitrogen, and oxygen-containing compounds through hydroprocessing. This process occurs under pressures ranging from 30 to 80 atmospheres and at temperatures between 572 and 752 degrees Fahrenheit, using catalysts such as nickel molybdenum or cobalt molybdenum compounds. As a result, sulfur content is reduced, minimizing corrosion and harmful emissions. Additionally, fuel stability improves, allowing for longer storage without sediment formation. If crude oil does not contain enough kerosene fraction, catalytic cracking or hydrocracking is used to break heavier fractions into lighter ones. Catalytic cracking employs catalysts to break large molecules into smaller ones, while hydrocracking uses hydrogen to produce stable hydrocarbons. These processes help increase the yield of kerosene for jet fuel. After purification and modification, special additives are added to the kerosene fraction to enhance its properties. Antioxidants prevent sediment formation and maintain fuel system cleanliness. Anti-static additives reduce the risk of electrostatic charge buildup during refueling. Anti-corrosion agents protect fuel tanks from corrosion. Anti-freezing additives ensure stability at low temperatures. After additives are introduced, the fuel undergoes final filtration and preparation for distribution. To meet international standards, jet fuel undergoes strict quality testing. Viscosity determines fluidity at low temperatures. The freezing point for Jet A1 must not exceed -52.6 degrees Fahrenheit. The heat of combustion must be at least 18,400 British thermal units per pound. Water content must not exceed 0.462 thousandths of a grain. Electrical conductivity ensures safe refueling without sparks. If the fuel fails to meet standards, it is sent for reprocessing. And now, we reach the final stage of our journey. The finished jet fuel is stored in tanks with moisture and temperature protection. It is transported primarily through pipelines to airports. Large volumes are shipped by rail tankers. Tanker ships handle international deliveries. Trucks deliver fuel to remote airports. During transportation, it is crucial to prevent contamination with water or foreign substances that could compromise fuel quality. By the year 2025, the United States is projected to consume nearly 2 million barrels of aviation fuel per day, totaling approximately 86 million tons per year. As one of the world's largest consumers of jet fuel, the global demand is expected to be significantly higher. The aviation industry is actively working on developing renewable jet fuels to reduce greenhouse gas emissions and improve sustainability. With advancements in technology and environmental regulations, the future will see wider use of biofuels and synthetic alternatives, making aviation more eco-friendly. And most importantly, jet fuel keeps airplanes flying. The next time you board a plane for a vacation or business trip, remember the complex production process that brought that fuel to the aircraft. I think it is worth it. What do you think?